Welcome to a new chapter in geometry. I hope this video finds everybody healthy and doing well. Today we get to start the study of one of my favorite topics within mathematics, which is talking about constant ratios and right triangles. And so today what we're going to do is we're going to look at slope triangles specifically. And so today we're going to draw some stuff. We're going to be using angles, Pythagorean theorem, triangles, kind of all of this idea in order to talk about slope triangles within context. And so today is really the start of our study of what's called trigonometry, which I think is really kind of cool. And the backdrop for today's lesson is the Leaning Tower of Pisa, and maybe people have seen that quite frequently. But I'm just going to read the first heading here on problem 4-1, and you can follow along with me. And it says, for centuries, people have marveled at the Leaning Tower of Pisa due to its slant and its beauty. Ever since its construction in the 1100s, it's slowly started to tilt further and further south, and it's at risk of falling over. It's feared that if the angle of slant, so this angle down here as the arrow is pointing, if that ever falls below 83 degrees, the tower is going to collapse. So engineers closely monitor the angle with a tower lens, and with careful measuring, they know that the point labeled A in the diagram is 50 meters off the ground. And so then they also have this measurement of 5 meters from the base of the tower. So the first question in question A says, with the measurements provided, what can you determine? Well, the first thing that I want us to highlight or to understand is you can draw this whole picture of the triangle with the Leaning Tower of Pisa next to it within your notebook if you're keeping track at home on a notebook. And we're going to use triangles to help us determine how tall the Leaning Tower of Pisa is. Notice that this length right here, this vertical length, is not the height of the Leaning Tower of Pisa. The height of it actually is going to be the distance from A, the very top, is this slanted height right here. So what we're going to do then is we are going to determine what that slanted height is. And so if I were to draw the triangle a little bit off to the side over here, ooh, that is not good, ladies and gentlemen. We're going to give that one another try. This is a vertical distance and comes down like this. Here's my right angle. I know that this distance is 5 meters, and then this distance here is 50 meters. If I wanted to find this distance right here, remember, if we have two sides of a right triangle, we can use the Pythagorean theorem. So I'm going to set up the Pythagorean theorem, and I'm going to use that to help me solve. So using some of our tools that we have in our toolbox, I use the Pythagorean theorem, and I did my work for Pythagorean theorem here. And so 25 plus 2500, 5 squared plus 50 squared turns out to be 25. 25 equals x squared, take a square root, and what we determine is that the height of the Leaning Tower of Pisa is roughly 50.25 meters, and that's something that we can do based off of our work in previous problems. And so what I want to do then is bring this back into a focus over here, which would be letter B. It says, can you determine the angle at which the tower leans? And the answer to that is no. We don't have any tool mathematically yet within our grasp that's going to allow us to be able to determine this angle right here at which the tower is leaning from. And that's actually what we're going to do moving forward from today. So at the end of section 4.1, you're going to know how to do that. That's what part C says. It says, however, at this point, how else can you describe the lean of the tower? And what I want us to start to be able to envision, and what we're going to do for kind of the next day or two, is talking about slope. Okay, and so when it comes to the slope, remember we like to think of slope as rise over run. And so that's something, if you forgot, to be able to write down again in your notebook. Slope of a line is rise over run. So if I was to look at the slope of the red line, this line right here, I could describe that as the change in y over the change in x, or its rise over run, which in this case is going to turn out to be 50 over 5. And I can simplify that to be 10. Okay, so the slope of that line would be 10 units, and this is a very profound mathematical term when it comes to triangles and the slopes of the hypotenuse, and this is something that we're going to develop further and further as we move forward. moving on to problem 4-2, it says, in order to find an angle, which is what we wanted in the Leaning Tower of Pisa, it says you need to investigate the relationship between the angles and the sides of a right triangle, just like what we did when we found the slope being 10. You're going to start by studying slope triangles. Obtain a resource page from your teacher. You don't have that resource page unless you go to the Canvas page and you download the schedule, the Chapter 4 schedule from Canvas, and then it's on there. You can just do this in your notebook on the graph paper that you have. It says down below, notice that one slope triangle has been drawn for you. In the next several lessons, angle measurements will be rounded to the nearest degree. So it says draw 3 new slope triangles on each line. Each one should be different. And so what they're trying to get at in this problem is that, hey, we have something that measures 11 degrees down here. And we can draw on this slope triangle of going over 5, up 1. That creates a right triangle within that that given line that we have. And so what we're going to try and do is we're going to draw another slope triangle that is different from 1 and 5. And so what I'm going to do is I'm going to pick another nice point that this thing goes through, like that. And I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to have this line go all the way over here, and you'll notice that if I were to go over 10 units and up 2 units, I get another nice triangle that fits on some nice grid points or something. Now we could continue to draw several slope triangles within that picture or within that frame, but we're always going to end up getting this ratio of triangles having 1 over 5, the rise over run, or 2 over 10, or if you drew another one, you might have turned out to get something that's like the same equivalent ratio of 1 over 5, or 2 over 10, or 3 over 15, if you will. And so the question B asks, why are all the slope triangles similar in this instance? Well, all of the slope triangles are similar because of angle. And I know that because the angle that is right here is a right angle, as is this angle right here, and they both have a measurement of 11 degrees at this point right here with the line and its horizontal component. So all the triangles are similar by angle. They're not the same size, but they are the same shape. And so since the triangles are similar, what does this tell you about the slope ratios? What is this true about these ratios since these triangles here are similar to one another? And so what that means is that these slope ratios must be equal to one another. And so that's an important point. And so it says, confirm your conclusion by writing the slope ratio for each triangle as a fraction, such as the change in y over the change in x. And we actually just did that. I did that up here. 1 over 5 and 2 over 10, those are the same ratios. Or if you did 3 out of 15, that would continue to be the same ratio if you went over 15 and up 3 units. And so since we have similar triangles due to angle, all of the slope ratios of those triangles are going to be the exact same. And we're going to use that point moving forward. So Tara starts to see a pattern in these slope triangles, and we're looking at problem 4-3. So she decides to make some changes in order to figure out what's going on. She says, what if I draw a slope triangle on this line with change in y being 6? So as a reminder, our change in y over change in x in that last problem was 1 over 5. That's the simplest form that we had, or the same thing, which is 0.2 as a decimal. So Sarah now, Tara in this instance is saying, well, what if I have a triangle with a change in y of 6? Well, if I were to have 6 over something, and I know that needs to equal 1 over 5, since these slope ratios need to be the exact same, those need to be equal to one another, I can change this to just more or less be a variable. And what I can do is I can cross multiply. And after I do that, I'm going to get x times 1, which is just x, and then I'm going to get 30. So I know then that my change in x would have to be 30. And so if I rewrote this change in y over change in x, I know that that would turn out to be 6 over 30 I just now found, which is that same ratio of 1/5, or 0.2. So Now she continues in a similar manner on part B up here. It says, well, what if the change in x is 40? Then what is the change in y? Well, we can continue that same process like what we did up above. I know that if the change in y over the change in x in that 11-degree slope triangle is 1/5, and I know in this particular instance the change in y we said is going to be 1, or excuse me, we don't know what it is. I'm going to call it question mark, but the change in x is 40, and that has to be equivalent to 1/5. We can follow again a similar principle of multiplying across. And so I have 5 times something equals 40. And if I were to divide both sides by 5, I know then that that something is going to be equal to 40 divided by 5, which is 8. And so therefore, my change in y over my change in x would be equal to 8 over 40, which again, if you type that into your calculator, is going to be 1/5 or 0.2. So even though we don't have a specific value for some of these up here, like an A or B, we can find those, understanding that the slope ratio needs to be constant for 11 degrees of 1/5. So Tara then wonders at the end, well, what if I draw a slope triangle on a different line? Can I still use the same ratio? And what she's talking about is that if you have a line that goes like this, where the change in y over the change in x is not the same as your line that you drew here, you can't use the same triangle, okay? The triangle isn't going to have the same ratio as your change in y over change in x is obviously going to be different. So this problem, where we have the 11 degrees and the 1/5 as our change in y over change in x, that only works whenever our angle with the line is 11 degrees. So finally, on problem number 4, what we're going to do is we're going to revisit the end of the previous problem. It says, what if I draw my triangle on a different line? It says, with your team, investigate what happens to the slope ratio and slope angle when the line is different. So in part A, what we're going to do is we're going to graph y equals 2/5 x. And as a reminder, if I have y equals 2/5 x, remember that was the slope, change in y over change in x of my line, 2/5. So as I go to graph that on this graph paper below, I will go through the x-axis, and so I'm going to go up to, or excuse me, go through the origin, I misspoke. Then I'm going to go over 5 units right here, and so that line is going to go up to over 5 continually, and it's going to look something like this as it goes through the origin. And so if I were to draw in a triangle, a slope triangle, notice that I still have 5 as my run, but now my rise is 2. And so this angle measurement down here is actually now 22 degrees. It's no longer 11 degrees. And so the question says, does the information from this line support or change your conclusion from part C? Yeah, it does, because if I drew this different line, it's not the same slope triangle of 1 and 5 like we had in the last problem. So it is a different slope triangle for a different line. On graph B, it says you're going to create angle QPR, so it measures 18 degrees. That's kind of hard since you don't have a protractor or you don't have a clinometer, which is another name for something. So you don't need to worry about that. What we are going to do is go to part C here rather, and we're going to look at graphing the line y equals x plus 4 and draw a slope triangle and label its horizontal and vertical lengths. And so in part C, we have the line y equals x plus 4, which again is a linear equation, and this slope, my change in y over my change in x, is 1/1, and this is my y-intercept at the point 0, 4. So this thing is going to start right here at the point 0, 4, and it's going to go up 1 over 1. Whoopsie, that was not very good. Up 1 over 1, up 1 over 1, up 1 over 1, and so this line is going to go something of the sort. And so if I were to draw in slope triangles, I think you would recognize that I'd go up 1 over 1, or you could go up 2 over 2, and all of these ratios of my change in y over my change in x is going to be 2 over 2 or 1 over 1, and all of these equate to just be 1. And so if you wanted to recognize something special about this, when we have a slope of 1, notice that these two side lengths here are the same, and that's the same in this triangle down here. These two side lengths are both the same, and what is true about two sides of a triangle when they are both the same? If I have a triangle with two of the exact same side lengths, 2 and 2, well, we have a special name for that kind of a triangle. This is an isosceles right triangle. And so one other little tidbit of information that we can fill out when you have a slope triangle with two of the exact same vertical and horizontal components, well, I know that this angle is 90 degrees. Well, these angles here and here have to be the same measure since the triangle is isosceles. And since they have to be the same, they're actually both going to be 45 degrees. And so one final connection that we're going to draw with these slope triangles is that when you have a slope of 1, or when you recognize that your horizontal and your vertical component are both the same value, you're going to turn out to have an isosceles triangle, or in other words, this angle right down here is going to be 45 degrees. So the angle in which this is going up, this base angle is 45, as is this one, and so forth. So to summarize today, what we just talked about was the slope of a line, which is the ratio of its change in y over change in x. This first paragraph up here does an excellent job of recapping that, and I think it would be worthwhile in your notebook to draw in this triangle right here, especially with this little weird looking thing down there, and that's pronounced theta. It's a Greek letter, and it represents an angle measurement, and so that's pronounced with a th, theta. And so that's going to represent our angle measurement. It's like a variable for your angle from here on out. And so we can say that theta, whatever the angle is right here, what we've been describing that slope triangle as would be the change in y over the change in x. And so that's something that we're going to be using as we move more and more here on out. And so the big idea from today is that we can create slope triangles with right triangles and know that the change in y over the change in x is a slope ratio for us. And we're going to see how it applies to right triangles moving forward. As always, you can feel free to swing by my office hours. Just go to Canvas and click on the link. Otherwise, I hope you have a great day and stay safe and stay healthy.